Case study number 3 of finite element methods. The group is made up of Ana Fandino, David Moyano, Miguel Rodriguez, Julian Delgado and Alex Farfan. The study of this piece is important, since it is essential for the connection between pipes, which allows the failure to be selected on its own and not affect the pipe as such. In this case, the dimension that you want to vary to verify its reactions is the thickness of the base. Furthermore, in the analysis we want to reduce the mass and increase the safety factor for manufacturing cost purposes. This piece has an embedment in its lower part and in its upper part it has an acting force of 37 kilonewtons, which was found thanks to artificial intelligence, since this is the approximate load to which the pipe supports are subjected. The original length of the piece thickness is 15 millimeters. A variation of 10.5 will be made millimeters up to 19.5 millimeters with increment of 1.5, and it is evident that there will be a percentage of change from -30 to 30%. The three materials that will be studied are structural steel, aluminum and titanium. In each case, the thickness and mass increase and therefore the safety factor increases proportionally, since a greater thickness generally becomes more resistant to deformation, fracture or collapse under applied loads. This increase in resistance translates into a greater safety factor in the simulation. A 5 mm mesh was made with a multi-zone method so that the mesh is better generated throughout the entire figure and its resolution was 6. In all three materials, the maximum stress is evident at approximately the same point, since this is a stress concentrator due to an abrupt transition in the shape of the piece. Furthermore, it is evident that titanium has an excellent capacity to absorb energy and resist impacts, since its maximum stress is the lowest of the three materials. The best option according to ANSYS for aluminum and titanium structural steel is option number 3, which has a thickness of 12.5 millimeters. Each one has a mass and a safety factor equivalent to it. According to the results, comparing the three materials, the best is titanium, since it generates the best safety factor, however it is the most expensive, therefore in terms of cost-benefit, the best is aluminum.